Good morning and welcome back to another episode of Teaching Math 2.0. In this episode I will explain how Pythagoras can be used in different situations and I will teach you how to draw auxiliary lines. I hope you've done your homework and practiced the Pythagoras theorem because we'll be using it a lot this chapter. So let's start paragraph 5.3, applying Pythagoras' theorem. By now, you should know how to use the Pythagoras theorem to calculate the side of a right-angled triangle. So, for triangle ABC, the theorem goes AB squared plus BC squared is AC squared. We fill in the 12 and the 45 to receive 12 squared plus 45 squared is AC squared. This gives us 144 plus 2025 is AC squared. So AC squared is 2169. Then we take the square root of 2169 to receive 46.6. But, as I already told you in the previous episode, you will not always be given a simple question like this. Pythagoras could be hiding in a situation such as this one. This is a plot of land in the shape of a trapezium. Side DE is 120 meters, FG is 70 meters, and DG is equal to 80 meters. Let's find the perimeter of this plot of land. We already know 3 of the 4 sides, so we only have to figure out the length of the line segment EF. To figure this one out, we draw an auxiliary line from F perpendicular to side DE. This will create a right-angled triangle SEF. Side SF is equal to DG, so 80 meters. Side SE is the difference between the 120 meters and the 70 meters, which is 50 meters. With Pythagoras' theorem, we can calculate the length of EF. ES squared plus FS squared is EF squared. 50 squared plus 80 squared is EF squared. 2500 plus 6400 is EF squared, which means EF squared is 8900. EF is equal to the square root of 8900, which is rounded off to the nearest integer, equal to 94 meter. Now that we know all 4 sides, we can calculate the perimeter of the land by adding all the sides. 120 plus 94 plus 70 plus 80. So the perimeter is equal to 364 meter. A different shape we will encounter this paragraph is the isosceles triangle. For example, triangle KLM, where KL is equal to KM, is equal to 5 centimeters. We also know that LM is equal to 8 centimeters. If we were to calculate the area of the triangle, we use the formula half times base times altitude. As you know, the base of a triangle is one of the sides and the altitude is a line segment perpendicular to that base through the opposite vertex. So, for side LM to act as the base, we need to figure out the length of this line segment. Luckily, we can use Pythagoras' theorem to figure this one out. We turn our attention to triangle KTL, where KL is 5 centimeters. As point T is in the middle of LM, we can conclude that LT is 4 cm. We use these numbers in our theorem. KT squared plus LT squared is KL squared, followed by KT squared plus 4 squared is equal to 5 squared. Then KT squared plus 16 is equal to 25, which means that KT squared is 25 minus 16. Which is equal to 9. We then take the square root of 9, which is 3, meaning the height of this triangle is 3 centimeters. We now have a base and a matching altitude, so we can finally calculate the area of triangle KLM. Half times 8 times 3, which is 12 centimeters squared. To summarize, Pythagoras can not only be used in right-angled triangles, but also in trapeziums and isosceles triangles, with a little help. So, ready for one more? Then take a look at this picture. Clark and Lois want to buy a tiny house. They settle on a gambrel design. That's a type of roof as shown in the picture. Your assignment, should you accept, is to calculate the height of the house. Good luck! What we want to know is this line segment. We see that part of the height overlaps with the first floor and the support beam over here. That means we have to figure out the length of that support beam and the height of the top triangle. We start with that last triangle as we already know all dimensions. The two legs of the isosceles triangle are 2250 mm and the base is 4000 mm. By drawing an auxiliary line from the top, placing letters and writing the length of side AB, we are now ready to use Pythagoras to calculate the length of side BC. AB squared plus BC squared is AC squared. We fill in the numbers, calculate the squares, calculate the remaining square and take the square root. BC is the square root of 1,062,500, which is equal to 1030.7 millimeters. Now onto this line. Of triangle DEF, we know that DF is equal to 3200 millimeters, and we want to know side EF. But the problem here is that we do not know the length of side DE. Luckily, we can figure it out by looking at all the horizontal lines. We know that the roof extends 200 millimeters on both sides, meaning the house is 6800 millimeters wide. By subtracting the 4000 millimeters from the middle and then dividing it by 2, we calculated that side DE must be 1400 millimeters. We now use our 1400 and 3200 millimeters in our theorem. DE squared plus EF squared is DF squared. By filling in the numbers and calculating the squares, we know that EF squared must be 10,240,000 minus 1,960,000 is equal to 8,280,000. And EF is then the square root of 8,250,000, which is approximately 2,877.498 millimeters. When rounded to the nearest integer, this means our house is 2,300 plus 2,877 plus 1,031, which is equal to 6,208 millimeter, which is approximately 6.2 meters. And with that, we've reached the end of this paragraph. To make sure you won't do anything wrong, let me show you how to not divide a trapezium. For the trapezium, cut it like this. Always. Do not cut it like this or like this. Especially not like this. These lines will never help you with your goal, whatever that may be. This may seem like an easy paragraph, but make sure you practice enough. Make sure you know how to correctly draw an auxiliary line and how to incorporate Pythagoras in your calculations. And, last but not least, always make sure you correctly round off your answers. In the next paragraph, we'll be making a start on 3D figures. Specifically, I will explain what cross-sections are and how to draw them. So be sure to tune in next time. Bye bye!